Right. So the plan is the following. I will talk about two stochastic processes that apparently have not much in common at first sight. One is the diffusion in the curl of the two-dimensional Gaussian free field. The second one is a version of the two-dimensional KPZ equation. And then we'll see that what is the common feature of this is that they show certain superdiffusivity phenomena that are logarithmic and actually with the same, really of the same type of the square root log t superdiffusivity that you see in the subtitle. And then, okay, I will tell you a bit about the conjectures results, and then try to put these results in a larger framework of logarithmic superdiffusivity in other contexts. All right, so let's come to the first stochastic process. This is a diffusion in a random environment. So you think of a particle in two dimensions. The position of the particle is 0 at time 0. At time t is xt. And well, the way it evolves is that there is a Brownian part, dBt, plus a drift part. So the drift is omega. Omega is some vector field, two-dimensional. So okay, so the drift is x omega of t, and then dt. Very good. So omega is, as I said, is a time-independent random vector field. I will denote with this double bar p the law of this environment. And what is more precisely the environment? The environment is roughly speaking the curl of the two-dimensional Gaussian free field xi. So let's see more precisely. So this driving field has two components, omega 1, omega 2. Omega 1 will be the derivative with respect to the second space component of xi. I will say in a second what xi is. Omega 2 is minus the derivative with respect to the first component. So you can write this as a curl of this scalar field xi. And what is xi? Xi is a regularized version of the Gaussian free field on the plane. So first you start with the Gaussian free field on the plane. Let's call it xi tilde. This is a Gaussian center Gaussian distribution, such that well, if you test it against a test function phi, then xi tilde of phi is simply a Gaussian random variable of average 0 and of variance the h-1 norm of phi. This is a two-dimensional Gaussian free field. So it's well known not to be a function; it's irregular. So in order to have an equation which is perfectly well defined, we simply regularize it in space. So we call xi without a tilde simply the space convolution of the Gaussian free field with some approximate delta function u. So u is some bump function, say rotationally symmetric, smooth, I don't know, compactly supported, something like this. You convolve xi tilde with that. Now you obtain a field xi, which first of all doesn't have a tilde, and more importantly is smooth. So now xi is really a function of space that is as smooth as you like. Okay, and now given that xi, you define this vector field omega 1 omega. Okay, so this is the driving field. Okay, good. So we have a diffusion in the let me maybe draw. Okay, do something. So if you look at how this equation is defined, you will see that, imagine, okay, so here I will draw a picture. Imagine I draw the level lines of this field xi. I mean, it's some scalar function, we have some level lines. And you can check quite easily that this vector field omega is parallel to the level lines. It's orthogonal to the gradient of xi, so it's parallel. So somehow this vector field drives the particle along the level lines of this random field, but there is also the diffusion part that tends, I mean, just drives you away from the level lines. So there are these two very different effects: the diffusion plus somehow this random field that drives you along the level line. So what happens to this particle? Very good. So what are the questions? The question is about the large scale, especially large time behavior of this diffusion. Actually, is it really diffusion? Is it really diffusive on large times or large scales, or is it maybe super diffusive? Well, I guess it will be super diffusive. And actually, there was a conjecture. This model was introduced by, I would say, towards about the history later, but was introduced in a paper by Balintot and Benedek Valco in 2012. And they conjecture, they have a heuristic argument to conjecture that the behavior will be super diffusive, but barely so. So if you look at the mean square displacement of the first of all, there is symmetry. So the mean position, the average position at every time is 0. So if you look at the mean square displacement, where here this average is in a sense a joint, so how do you call it, quenched average. So you average with respect to the Brownian noise and the environment. Then they conjecture it to grow like t times square root log t. Okay, so slightly more than diffusive. And all right, so this is the conjecture. And an important remark here is that if you look at how the driving field is defined, you will see that it is pointwise divergence-free. So you just compute the divergence, you will see that it's 0 pointwise, plus the law of the environment is ergodic. And in this case, it's well known that if you follow the particle, then the environment seen by the particle, I mean, the law of the environment seen by the particle is P at all times. So P is the invariant measure for the environment process. This is really important. And I mean, it's well known, but it's really essential. Okay, very good. This is the conjecture. So let me, okay. So what did they prove? They proved that a result which in a sense is much weaker than the conjecture, but it's already quite interesting because it shows the superdiffusivity. In fact, they have a lower bound on the mean square displacement divided by t, a lower bound of order log t. It's quite slow, but still diverges with t. And then I also had an upper bound of order log t. Remember, the conjecture is square root log t. As usual in this business, these results are proven in a Tauberian sense. So what actually one is able to handle more easily is the Laplace transform of the mean square displacement. You'll find it as usual, d of lambda. And then what one, this d of lambda is easier to control directly rather than the mean square displacement. So what they actually proved was that for lambda small, which corresponds to large time, this d of lambda behaves like 1 over lambda squared times corrections which are at most log and at least log in lambda. Okay, so it's really okay. So think of the result in blue, but actually what is proven is the thing in black. And in terms of the Laplace transform, the conjecture then would be that this Laplace transform behaves like lambda to the -2 times square root of lambda as lambda goes to 0. It's just translating the conjecture in Laplace sense. Okay, so here so here is our result. This is working collaboration with Giuseppe, Levi, and well, from last year. Essentially, we prove exactly the conjecture up to log correction. So what you see here is this ratio d of lambda over square root log lambda times lambda square. The conjecture is that this combination is of order 1 as lambda goes to 0, while what we can prove is that it's of order at most log. So somehow the main point is that d of lambda has this square root log divergence, and then there are log corrections that we cannot rule out. I mean, we don't believe this is an actual effect, but I mean, it's more like an effect of the proof. Okay, good. Well, maybe you don't like Laplace transform too much. So what can one say if for the real time mean square displacement? For upper bounds, there is an easy, I mean, a very nice but quite simple argument by Castel and Valco that allows to translate the result into real time. So once you have the result in Laplace, then you can actually deduce that the mean square displacement grows at most like t times square root log t times this log. As for lower bounds, in general, you cannot obtain a pointwise in time result, but you can prove that in some weak sense, also lower bounds hold. For instance, as a limb, you can prove that the limb sup as t goes to infinity of the mean square displacement is larger than, I mean, divided by t square root log t log, etc. is positive. So if you allow for limb sups, then this is telling me that really the mean square displacement is of the order of t times square root log t times this correction. Okay, so but the real work is to get the result in Laplace. Then the rest is quite standard. Okay, so this is the first. This is the first process, the first result I wanted to present. The second, well, interrupting me anytime, of course. The second one is a priori totally unrelated. We will see the relation in a moment. The second one is a variant of the KPZ equation. So the KPZ equation, you know, is an equation for a scalar depending on space and time. And okay, let me introduce directly this anisotropic two-dimensional KPZ equation. It looks like this. You have a function of space-time. Space is two-dimensional. Time is, well, time is time. And then you have an equation of the type dth equal Laplacian h plus, okay, psi is a space-time white noise plus a nonlinearity. And the nonlinearity is, in this equation, it looks like this. It's a gradient in direction 1 squared minus gradient in direction 2 squared. Okay, fine. And in front of the nonlinearity, there is some coefficient that you can tune to get to change from the linear to the nonlinear equation, this lambda. Okay, if instead of this minus sign in the nonlinearity you had a plus, then the nonlinearity would simply be the gradient square of h, and this would be exactly the KPZ equation in 2 dimensions. Okay, but we have a minus, so it's really important that we have a minus. The second point, everyone knows that KPZ equation is ill-posed, but one can regularize it. And so I will not write it in the equations, but suppose it has been regularized. Either you convolve the white noise in space, or you, which we actually do, or you regularize the nonlinearity in Fourier. So there is a standard procedure of making this equation well posed by some regularization. And then the question, okay, once you regularize it, I mean, the job is not done, because then the question is, how does this process behave on large scales? In particular, is it diffusive? Is it super diffusive? Again, like for the previous one. And there are two important remarks. First of all, okay, let me make first the second remark. Well, I don't know. So the first important remark is that was made in a couple of years ago by Cannizzaro, Erhard and L is that this nonlinear SPD doesn't matter what the nonlinearity parameter lambda is, its stationary state is just a Gaussian free field in 2 dimensions. This is important, and it's really non-trivial symmetry of the equation. It's based on the fact that this equation satisfies the symmetry that if you change h to minus h and you change x, say x1 to x2, so you make a change of like flip the coordinates x1, x2, and at the same time you change the sign of h, the equation is invariant, which is not the case for the usual KPZ equation. Okay, based on this, one can prove that the Gaussian free field is stationary for this equation. This is very important. The second observation is that if you drop the nonlinearity, so if lambda is 0, then the equation, at least on the infinite plane, is exactly scale invariant under diffusive scaling. So if you divide space by epsilon and time by epsilon squared, the equation will be, in law, will be the same. Now, the question is whether once you have nonlinearity, the equation is still at least approximately scale invariant under the diffusive scaling or not. This is the main question we addressed here. And okay, so I will give, for reason of time, a very, very informal statement of the theorem, which is really, okay, so there is an actual theorem behind, but this is best I can manage to do. So take your solution, if it exists, we have regularized, and do the diffusive rescaling. So call H epsilon this rescaled solution. And remember, for the linear equation, this H epsilon actually in law does not depend on epsilon. And now take this H epsilon and test it against some test function phi. And then what we can prove is that this time is with Giuseppe and Dirk, is that as soon as you have the nonlinearity, as soon as lambda is not 0, the solution of this equation decorrelates in time extremely quickly. So this H epsilon at time 0 and H epsilon at time t are essentially uncorrelated as soon as time is of order of 1 over square root of log of 1 over epsilon. This goes to 0 as epsilon goes to infinity. So this is somehow, it means that once you put the nonlinearity, notice that if lambda were 0, then we said that H epsilon does not depend on epsilon in law. So in particular, this is a perfectly well-defined stochastic process that has a law that doesn't depend on epsilon. So in particular, these two random variables would decorrelate on a time of order 1 because epsilon does not appear in the law. As soon as you put the nonlinearity, somehow you have this fast decorrelation. Well, fast, I mean, it depends if you consider that 1 over square root of log is small or not. But these two random variables decorrelate on a time which is going to 0 asymptotically with epsilon. So somehow something different happens. This is telling you that the process is not scale invariant, even asymptotically for large time. Okay, so this is a very informal statement of the second result. What we actually prove is a certain result for the bulk diffusivity coefficient of the equation, which I will not introduce here, but just I think this is the most intuitive way I have to formulate the theorem without much notation. Okay, so what do these two models and two theorems have in common? So look at the first one, the diffusion. Of course, you can integrate in time the equation. So you integrate from time 0 to time t, you get the position at time t is bt plus the integral from 0 to t of the driving field omega of xs ds. Okay. You can do something similar for the KPZ anisotropic KPZ equation. You integrate in time and you get that ht of phi equals the same thing at time 0 plus the integral from 0 to t of the equation, the linear part of the equation, plus lambda times the integral from 0 to t of the nonlinear part of the equation. Okay, no big deal. So to unify somehow the two models, call Vt either the drift for the first model or the nonlinearity for the second. Okay, there should be a t here, not s. Just to write the two with the same symbol. Then somehow it's pretty obvious that, at least for the first model, it's completely obvious that if the second term coming from the driving field is much larger than square root t, so if its variance is much larger than t, so this term will dominate in the behavior and the process will be actually super diffuse. Okay, so if its variance is much larger than t, then the bt is totally irrelevant for t large, and well, xt will have a variance that is much larger than t, which is what I mean, this is super diffusivity. Okay, and okay, so for the second equation, maybe it's less obvious, but there is a similar argument. So the point is to understand how big is the variance of this time integral. Now there is a classical estimate. Well, a classical, I put the quotes because actually the actual estimate that I have in mind is actually expressed in Laplace transform. But okay, apart from this, morally this is a classical estimate. If you look at the variance with respect for the stationary process of the integral from 0 to t of this function vs ds and divide by t, this can be bounded by the average of v times the inverse. Okay, let's read this formula. We have v, then the inverse of 1 over t minus L0 times v again. What is L0 is simply the symmetric part of the generator of the process. Here for the diffusion, it would be the generator of the environment process. And 1 over t is simply 1 over t. Now, okay, so this is an inequality. It probably has a name, I'm not sure. And now the point is that now the right-hand side, you can compute. The symmetric part of the generator for the two models is quite simple. You can compute this expectation, and it turns out after some computation that this behaves like the integral. You have to go in Fourier space, so the integral becomes an integral on momentum, and it turns out to be of the form of an integral in dp of 1 over p squared plus 1 over t. Okay, and now since we are in dimension 2, this integral is divergent for t going to infinity, and well, it's quite pretty obvious, pretty easy to see that this integral diverges like log t. So the classical estimates would just tell you that the variance of this term is upper bounded by something divergent. Of course, this is just an upper bound, so this doesn't imply anything. But what I wanted to point out here is that you get the same type of upper bound for the two models. So this is another similarity between the two. Oh, by the way, this upper bound you get, this log t, is not what actually appears in the theorem. So this variance in the end, it behaves like square root log t. So this upper bound doesn't give even the correct order, but still, it shows that something subtle is happening. And so, okay, so in both cases, you have that this average is logarithmically divergent for large times. And okay, somehow the natural analog of this process is in other dimensions, and somehow the dimension 2 is critical in the sense that this okay, maybe this will be a bit cryptic, but this divergence is logarithmic exactly in dimension 2, and while in higher or lower dimension, you would either get a converging thing or something diverging much faster. Okay, forget this remark if it was too quick. And right, so this is an important remark. So if you look instead at the diffusion in a divergence-free ergodic random vector field, if instead this norm here is finite even for t equal infinity, in this case one says that the h-1 condition holds. In that case, it's known that the diffusion will be actually diffusive on large scale, so that it satisfies a quench CLT. There are results by Komorowski-Olla in the discrete setting by Kozma Toth. I mean, there is a long literature here. So somehow this diffusion in the curl of the Gaussian free field is really at the boundary where this h-1 condition fails, because this integral up here would diverge for t equal infinity, but only barely fails. And this is the reason why this model was introduced by Toth and Valco to somehow have a simple, in a sense, nice model that is exactly at the boundary between the h-1 condition and the case where it fails. Okay, so this is the best I can say to show the relation between the two models. Let me to conclude, I think I have a couple of minutes. Let me try to put this result in a broader context of logarithmic superdiffusivity in two-dimensional systems. There is another model where such logarithmic superdiffusivity occurs. It's much more well known. It's the asymmetric simple exclusion processing on Z2. So think of ASEP maybe. Yeah, okay, so you take ASEP on Z2, which with an asymmetry of order 1, and then define what is called the bulk diffusivity coefficient, which is defined as follows. You sum over the positions in the lattice of the correlation between the occupation variable at time t and position x, and the same thing at time 0, position 0, times x squared, x is the position, you divide and then divide by t. So if you have the simple exclusion process, this would be of order 1 for large time. Instead, in dimension 2, this turns out to grow like a logarithm of t to the power 2/3. This was conjectured in the 80s by Van Beeren, Kuttner, and Spohn, and then was proven in a celebrated paper by Yao some 20 years later. Another example where logarithmic superdiffusion is expected is tracer particles in two-dimensional fluids. This was conjectured in the 70s. In this case, the corresponding diffusivity coefficient is conjectured to grow like square root log t, as in our case. The best result I know is for a lattice gas model studied by Claudio, Ramirez, and Yao some almost 20 years ago, where they prove a lower bound of order log t. Again, there is another case where this behavior is conjecture, is so-called self-repelling polymer. You have to imagine some Brownian, some diffusion that has a drift at time t, which is somehow the particle is pushed away from the places it has already visited. It has a drift that is proportional to minus the gradient of the local time. It's a self-repelling because it tries to avoid places it has visited in the past. And then this object in dimension 2 was conjectured again to be logarithmically superdiffusive. There was some controversy about the value of the exponent there, but the most convincing conjecture is that again you get the alpha equal 1/2. But again, the results here are quite weak. Toth and Valco proved log lower bounds and log upper bounds. And yes. So why do you have 2/3 for the ASEP and 1/2 for all the other models I mentioned? Well, this is hard to explain without entering the details, but there are really two universality classes with two different symmetries. So like the ASEP in 2D and the diffusion in the curl of the Gaussian free field really belong to have two different symmetries in the model. That it's okay. It's not obvious to maybe to see, but there is a reason why the two exponents are different. Okay, so I'm out of time. Sorry. So here I will not conclude, but leave some open questions. First of all, I've mentioned some other models for which this square root log t behavior is superdiffusion is conjectured. Lattice gases, 2D lattice gases, self-repelling polymers. It would be, I think. Okay, it's an open question to extend our result to these cases. There are additional complications that for the moment we were not able to overcome. For the diffusion in the curl of the GFF, what can one say about the quenched behavior? This is really for me totally open. I don't have a real conjecture. And for the anisotropic APZ equation, is it possible somehow to rescale the solution differently than diffusively with some log corrections, so that this process has a limit in the as epsilon goes to 0. That's it.
Well, thank you very much. We have time for questions.
Just about the last open question, is there at least a conjecture about what is non-trivial limit?
Actually, I think we are inclined to think that the limit in the end will be Gaussian. So will be some. Okay, it might still be that the limit is a linear stochastic equation with some renormalized coefficients. Yeah, it's a bit like in okay. The way we see it is it's a bit like a 5-4 model. Okay, if the comparison makes some sense. So in 4 dimension you have logarithmic corrections on the 2-point function, etc. But then on large scale the model is still Gaussian. So we find it quite likely that the limit process will just be Gaussian. So maybe it's just as the stochastic equation with additive noise. We're not totally sure, but this is what we think.
Other questions?
So thanks for the nice talk. So here my question: your techniques allow also to get some information, some bounds for higher moments. So you have considered mainly the variance, but can you say something for other moments?
Like for the diffusion? No, for the moment not. So this method really works well for the variance. The way we did it really, I mean, the nice thing is that you can write the second moment as at least in Fourier transform as in Laplace transform as the some inverse of I don't know, lambda minus L minus 1V, something like this. So this works well for the second moment. So what we use here doesn't work well for higher moments. On the other hand, okay, so on the positive side, something that I was not able to mention, did not have time to mention, is that for the anisotropic APZ equation, in another work with the same authors, we looked at the equation where at the same time where you do this, the diffusive scaling, you also multiply by the nonlinearity coefficient by something going to 0 as 1 over square root of log. Okay, it's a weak scaling of the APZ equation. In this case, we are able to control, not just to control the variance somehow, but to really prove that in that case the process tends to the stochastic equation. So in a sense, we are able to control all moments, but we don't do it moment by moment. We proceed differently.
Okay, thanks.
So thank you very much, Fabio, for this nice talk.